All right, so if you look up the Energy Skate Park simulation and see the graphs, all right, you can sort of see what's happening. And this is what we call usually a potential energy curve, all right? And there's sometimes problems that have this in it, okay? So we're going to go ahead and say there's no friction in this case, all right? But basically what you're trying to look at is if I have an energy versus position graph, you're going to see this kind of curved shape to it, right? So at the top, right, there's no kinetic energy. That's the dotted line, and it's all potential energy, okay? Right? And then at the bottom, okay, I'm going to have the lowest potential energy that I have, and I'm going to have the highest kinetic energy that I have, right? Because he's going to be going fast as he comes over the bottom, okay? And then going back to a similar place on the other side, right? And if no friction, then he's going to make it back to that same total energy point, okay? When you're looking at these graphs, you see, right, you can sort of add up, right, however much the kinetic energy is, right, and the potential energy is going to add up to the total, okay? And sometimes they ask you about this, what they call a disallowed or not allowed region, right? Any position past here, right, like, so if this is like a vertical position, right, top to bottom, anything past that max height is not going to be allowed, right, because he can never get higher than he was when he started, okay? All right, so here's another example kind of a potential energy curve. All right, it kind of looks like this. All right, and this is mathematically the important part. And again, don't overthink it too much if the math is confusing for you. Okay, some of you might actually see and understand the math really well, and some of you might be like, what are you talking about? Just kind of know how to do it, and then that'll be good enough for now, okay? All right, so you'll see what we call here a potential energy curve, which will have some kind of a shape to it, okay? And that's some ux. So instead of just being like mgh or 1/2 kx squared, now it's going to be actually a function with respect to position, okay? All right, and then usually they're going to give you this E total, right? What's the total amount of energy that's allowed, okay? And then they're saying in some initial position, right, I have this amount of potential energy because that's where the graph is. And then the rest of it would have to be kinetic. Okay, so I could solve that. So this has some potential energy and it's moving a certain speed. Okay, and then here, as this potential energy begins to start increasing, here we can see that the kinetic energy is getting smaller. Okay, but they still add up to the total. All right, and then when we're talking mathematically, this is kind of the important thing, okay, is that the negative, or the force is the negative derivative of the potential energy, okay? And all that means, right, remember derivative is slope, so the force is the negative slope of the potential energy graph. Okay, the force is the negative slope of the potential energy graph. And if that's wicked confusing, just know that that's how it is. Okay, so here, right, if I did tangent to the curve, slope here, right, that's a negative slope. So that would be a positive force. Okay, and you'll see in the next example how better. Okay, over here, right, if I have a positive slope, that would be a negative force. Okay, which you can kind of see, right, the kinetic energy is getting smaller. So that would be that there's like a force acting to slow it down. Okay. All right. All right. And then you can try these next two. Okay. But again, remember, this is the main thing. The force is the negative slope of that potential energy graph.